Hello everybody. I've spent last few vlogs talking about chain rings and cassettes, so let's switch gears and let's talk about wheels for a change. And the topic for today's video is why you are most likely going to break spokes on the inside of your drive wheel. And a fair warning, this is going to be an engineering heavy episode, so if you're not into that kind of thing, then skip to the end where the practical implications of what I'm going to be discussing are going to be presented. And let's start. And we're going to start with introducing the concept of a preload. You are feeling sleepy. Was that a really creepy Romanian voice? Anyhow, have you ever tried to carry a significant load using a piece of string? Well, of course you did. You hung something from a string from the ceiling or from wherever. And obviously the electromechanical, the atomic forces of the string were resisting the force you were pushing, unless the force was too great and you broke the string. However, have you ever tried to do the same with compressing the string? I guess not, so let's make an experiment. It doesn't seem like it's going to be very effective because the string gets all bunched up. So, how do we fix this issue? Well, we already did. Look at this. If I'm pushing gently from the bottom of this pendulum, then as long as the force I'm pushing isn't greater than the weight or the gravity created by the mass of this particular item, if the force I'm generating isn't greater than that, then the string remains essentially stationary. Now obviously this is a very light weight, so this effect isn't really great. However, it's kind of great in just about every mechanical device you have ever made, because this effect is called preload. It's used very widely in, well, engineering just about everywhere. The concept of a preload is kind of simple really, but here's how it goes. If you create a tension in a piece of something, in a string in this particular case, but if you ever tighten the screw, you are creating a force of friction between the elements of the screw, which is the preload, which is going to work against whatever this screw is supposed to hold. Anyhow, if you're going to create a tension in an element or in an item of some sort, then in order to deform that element, you need to first remove the tension from this element. Look at here. This string is being tensioned by this weight, and in order to bunch up the string like here, I need to first overcome the weight of the element. See? If I don't do this, then the string essentially is carrying the load and applying from here. And this, as I already noted, is called a preload, and you should start to expect that this is the effect that is being used in bicycle wheels. Hello there and welcome to the year 2025, where all animation has been banned because of what Disney has been doing in the year 2020. Anyhow, let's presuppose that this is a tire, this is a rim. Let's draw us some hub. Here we go. This is Dura Ace, as you can already see, because it's shiny, and those are spokes. Now obviously this is a cross section, if you haven't noticed yet. Stay there. Now, the wheel has been built, it has been tensioned, and the force of tension is acting in this direction. Also from the other direction, that's not really important, but we can write this as Ft, force of tension. Now we can decompose this force into two composite forces, or constituting forces, whatever. Force lateral and force radial. And what we also need to know is the angle between the spoke and the vertical line here, which is the angle of alpha. What can we for sure write about this particular situation? We can say that the FL, so force lateral to force of tension, equals sine of alpha. Now this is simple trigonometry now, isn't it? What we need to know from this formula is how much Ft actually is. So after certain transformations, we know that Ft equals force lateral divided by the sine of alpha. Okay? Okay, now what can we say about the force of tension? Now this is quite important because obviously as we were tensioning it, as we adjusted preload or added some preload, the length of the spoke had to increase because it's not infinitely stiff. Now the law, or the physical law that describes this phenomenon, is called Hooke's law, which in layman's terms tells us that the amount of deformation something is going to experience, or some item is going to experience, is proportional to the amount of force you're going to apply to that thing and the amount of thing you're having. However, in formal terms, Hooke's law is usually formed in this particular manner. Presuppose we have a rod of a length of L. Right. This rod has a cross-section, or the area of cross-section of S. It's made of some sort of a material, and we are pulling one end of this rod with a force of F. The other end is affixed to something. Now, what we can say for sure about this from the Hooke's law is that the amount of lengthening this rod is going to experience divided by the length of this rod equals the amount of force we are applying to it divided by the area of cross-section and the type of material the rod is made of. This is called Young's modulus. This is a constant that is describing the material of the rod. Now obviously the rod is a spoke in our particular case, so what we can further say from this particular, well, formula. Obviously in our case the F here is the force of tension, so what we can write for sure is that delta L to L equals Ft divided by the cross-section and E. Now this term looks kind of menacing, however this is essentially the percentage of deformation of the spoke, because if for example the initial length of the spoke or of the rod was, I don't know, 100 inches, and it has lengthened after applying the force by 1 inch, so it will be 1 divided by 100, essentially 100, so it's a 1% lengthening. So let's hide this. We are going to hide it by a value of percentage deformation, and we know that percentage of deformation equals Ft divided by S and E, the area and the type of material. Now let's replace the Ft here with this formula. So we know that the percentage of deformation equals F lateral divided by the sine of alpha, S and E. Now what we need to know is how much force lateral actually is. So after a few transformations we can for sure say that the force lateral equals percentage of deformation multiplied by the area of cross-section multiplied by the material constant multiplied by the sine of alpha. And this is important, so now we are going to switch the board to the other side. Alright, we're on the other side. This is the formula we have just derived. If you ever noticed how a bicycle wheel is built, you'll probably notice that it is two-sided. It has left spokes, so that's me here, and it has right spokes. This is whatever. The sides aren't really important, it depends on how you're going to look at it. Anyhow, it has two sides, and obviously the brace angle on both sides can be different. This is alpha R and alpha L. Not really visible now, is it? Anyhow, what we also can say about a bicycle wheel is that forces which are laterally pulling on the rim must be equal, because the rim isn't moving anywhere, and in order to satisfy the first Newton's law, well, they either have to be nothing or have to be equal. Since the rim isn't moving anywhere laterally, those forces are equal. So let's use this formula, but write it for both sides of the wheel. So what we can say? Well, the surface area on the left side multiplied by the percentage of deformation on the left side multiplied by the material constant of the spokes on the left side multiplied by the sine of alpha on the left side with brace angle must be equal to surface area on the right side multiplied by the percentage of deformation on the right side multiplied by the material constant of the spokes on the right side multiplied by the sine of alpha on the right side. Now from the get-go we are going to assume that the material on both sides is the same, so let's eliminate the material constant because it's going to be equal, right? Right, okay. So SL PdL times sine of alpha L equals SR, or SR, I am really messy, am I? Okay, SR multiplied by PD multiplied by sine of alpha R. Okay, what do we want to get to know from this equation? We want to know the relation between the PDL and the PDR. So let's transform this. Percentage of deformation on the left side divided by the percentage of deformation on the right side equals cross-section on the right side multiplied by the sine on brace angle on the right side divided by the cross-section area on the left side multiplied by the sine of alpha on the left side. Now what we can say from this formula is that if this part of this formula is equal to 1, is it visible? Yeah, it's visible. Okay. If this is equal to 1, then the wheel has been compensated for the dish of the wheel. Essentially, the angles of the spokes are irrelevant. If, for example, if the angles are the same, which means that we are dealing with symmetrical wheels, then the spokes can be the same, obviously, and this is going to be equal to 1. However, if these angles are different, then we need to compensate for this by using differently sized spokes in order to get this to a value of 1. If this value is different, either it is greater than 1 or is smaller than 1, then we are dealing with a dished wheel that has been biased to the left or to the right side. Why is this important? Well, let me explain to you. Alright, here's the mechanism. I have spared you from looking at me drawing all of this because, well, that was kind of a bloody process. I have spent an hour or so trying to work out my math here and here. Anyhow, I think I have realized my lifelong dream of being a scientist. I'm just going to, well... Anyhow, here's the cross-section of our wheel. These are the forces of tension on each side of the wheel. Obviously, this wheel is dished. Here's a cassette. If you haven't noticed, there's a... There you go. Now, in order to start our analysis, you need to first understand one very important thing. While the tension of the spokes is different on each side, once a load is applied from this direction, as I showed you here, the actual value of this load is going to be more or less identical on both sides. Because that's how geometry works, and that is because the angles on your typical bicycle wheels are usually very close to 85 or so degrees. They are something between 83 and 87 degrees, which means that their cosine, which is responsible for the amount of load that actually each side is going to carry, is going to be more or less, well, the cosine is more or less equal to something like 0.99. Anyhow, what we can gather from this is that if a load of 100 newtons is applied from this direction, which is essentially the load of riding the bike, then each side of your wheel is going to see 100 newtons of this load. That's a simplification, but it's going to be very close to reality. Now, let's start with a wheel that is dished and is tensioned in this way. The drive side sees 1200 newtons. and the non-drive side sees 600 newtons. That's a very pathological example, but a typical road rear wheel, which is non-disc, is going to see approximately 50% difference in tension. Alright, let's presuppose that the wheel has been built with this principle in mind. And let's presuppose that once we tensioned everything, the spoke on the drive side is 0.2 millimeters longer than its steady state. So once it's tensioned, it's going to lengthen by 0.2 of a millimeter. And likewise, because of the principle here, the other side is also going to be lengthened by 0.2 of a millimeter. Now let's get rid of this because it's going to be clouding our view here. Let's presuppose that we have applied 300 newtons of load to our wheel, like here. Obviously, because we can presuppose that the load is going to be equal and 300 on both sides, it's going to be applied, or it's going to lower the tension on the non-drive side by 300 newtons, which from Hooke's law we can already judge that it's going to end up with a spoke that is going to be 0.1 millimeters longer because the tension of the spoke has been lowered. Likewise, on the other side, the 300 newtons is going to remove precisely 300 newtons of tensions on the drive side, and we're going to get spokes that are going to be longer by 0.15 of a millimeter. Now obviously, from Hooke's law we can judge this. Obviously, a wheel cannot exist in this state because it means that the spokes on the drive side are longer than the spokes on the non-drive side, so the wheel has to balance itself. Intermission. I just realized that it's not really clear why the wheel has to balance itself. Imagine this is a perfect grid, not just hand drawn by me, and we've got two tensioned wires. This is the force of tension on the left, this is the force of tension on the right. Right. Okay, now we know that the lateral forces are going to work like this. Essentially this is a bicycle wire. Now let us apply a load. Let's draw it in green. Let's just apply a load of whatever here. Now, how much force are we going to see on each of these tensioned wires? Well, let's do a little vector drawing. You can see that this is on the non-drive side, this is on the drive side, and as I told you, those vectors are almost identical. This is why I'm simplifying it a bit. However, what are the lateral forces once we remove this force that removes our tension? Well, let's draw them. This is going to be this much, and this is going to be this much, which means that once we subtract this vector from this vector, there's going to be a bit imbalance here, and since imbalanced forces are going to cause some sort of movement, the wheel has to find a new equilibrium by getting rid of this imbalance and tensioning itself in a slightly different manner. So this causes the wheel to find a different equilibrium. Now let's return to our example. Alright, and the wheel has to tension itself in the new equilibrium. What is equilibrium going to be? I don't really know, but I am suspecting that this equilibrium is going to be somewhere between those two values. So let's presuppose that's going to be a lengthening of all the spokes by perfectly half of these. I'm pretty sure that's going to be somewhere about that. I'm going to have to do some really precise drawing to make sure. Anyhow, at this lengthening from the Hooke's law, we can judge that this side carries approximately 750 newtons of tension, and this side is still tensioned to 375 newtons. Essentially, the wheel is working from both directions. However, what happens, by the way, you should know that these values, when they are high, it's most likely good, especially if they are somewhat, well, different but the same. Yeah, anyhow, let's presuppose that we're doing the same thing with the wheel that is built with the equally sized spokes on both sides. From Hooke's law we know that if tension on this side requires 0.2 millimeters of lengthening, then the tension of this side is going to cause 0.1 of a millimeter of tensioning. So let's apply 300 newtons of load, and obviously from Hooke's law we know that this lengthening is going to shorten to 0.05 of a millimeter, and here we are going to have 0.15 of a millimeter because it's the same load. The wheel cannot exist in this state, it's going to find a new equilibrium. It's going to be more or less, once again, trying to find the same lengthening on both sides. So we're going to have an intermediate value, an average of these, which is going to be 0.1 of a millimeter here and 0.1 of a millimeter here. This means that on this side we'll see 600 newtons, and on this side we're going to see 600 newtons, which means that our non-drive side is not carrying any load at all, and the drive side is carrying twice the load that was applied to the wheel. And this is the reason why you're always breaking spokes on the drive side. And there you have it. And before all you competent people go to the comment section telling me that I am silly, let me just say a few caveats about all of this process. First of all, yeah, I hurt myself. Happens. 1. I am not a physicist, I am not even a mechanical engineer, and what I just described is me using a high school physics with high school vector arithmetics trying to describe a phenomenon I have noticed. Well, once I started building wheels in a certain manner. Because you see, I have told this story several times, but I would be having for years problems with spokes breaking on the drive side non-stop. It was something like a monthly occurrence for me because, well, I am big and heavy and I couldn't build my own wheels for quite some time, so it was kind of annoying when every wheel I would buy, even with the heaviest downhill specific rims, would be breaking spokes within a month or two. And the apex of all of this was when I was on vacation with my daughter. We were abroad, we were on an island, and there was a problem with our bicycles, well, being our only mode of transportation. And well, my daughter was in this little seat that's hanging off the bike, and well, that would be something like 180, 170, 150, something, quite a few kilograms being hung over the rear wheel. And we would have problems with spokes breaking within the first day or two, and it was kind of awkward trying to find a shop and repair a wheel and trying to avoid the cost that would be in euros. I would have to do it on my own. Kind of annoying. That was the moment when I said that something has to stop and I have to fix this issue once and for all. So what I've done after we returned from the trip is that I rebuilt the rear wheel using 2.3mm spokes, which would be twice the cross-section of 2mm spokes, and that didn't fix the issue because I would be breaking spokes less often, but still within a month or two of using that particular bike, especially when my kid was in that seat. So I sat one morning or evening or some other unknown part of the day. That was supposed to be quite poetic, didn't quite work. Anyhow, I thought to myself that if I'm breaking spokes on the drive side, let's use thicker spokes on the drive side. And so I did. And I haven't broken a spoke on that wheel since. And that was 2013. I'm still using this wheel, it's on my road bike, you have seen it. And I've been building my wheels using this principle ever since. Now, this wheel is 2mm on the drive side, 1.5mm butted spokes on the non-drive side, and I don't think I'm ever going to have a problem with it. And on my enduro bike I'm using the same, I think 2.3mm drive side and 2mm non-drive side. On my freeride bike I have 2.2mm drive side and 1.8mm, 1.5mm non-drive side. Point being, every bike I own, every bike I built for someone else is using this principle, and I haven't had a broken spoke on any of my rear wheels ever since. Something has to work. Now the problem is that how do I transcribe this instinctual understanding that something works to something that actually works? And well, you've seen the attempt. If you saw any issues with it, if you see some problems with my line of thinking, I'm all ears, because I'm one of those people who like to know rather than to be correct. I want to be correct because I know that I'm no. Number 2 in all those caveats post video kind of thing. What to do in practical terms, because that was quite a lot of engineering, but it's not really sensible to consider that someone is going to, I know, draw their own spokes because they need 1.85 millimeters on somewhere. Well, in practical terms, when you're building a wheel set, or where you have a wheel set getting built, insist on having a gauge or two on the drive side on the rear thicker than on the non-drive side. Even 1 gauge thicker is going to most likely, for most people, is going to work perfectly fine. If you want to be extra sure, or you are a Clyde or something like that, use 2 gauges thicker, or use the arithmetic I had shown you, and well, try to get the size of the spokes that are at your disposal to fit what the theoretical model is going to show you. However, in the simplest of terms, use a gauge thicker spokes on the drive side and you should be fine. Does any of the reputable wheel manufacturers do this? And the answer is, with 2 exceptions, one true exception, 2 possibly exception. I don't think so, but I haven't tried all the wheels on the market. But the 2 exceptions are, some fulcrum wheels are using this pattern of lacing, which is 1 spoke on the non-drive side and 2 spokes on the drive side on the rear wheel, and this is essentially the same thing because it uses twice the cross section of a spoke on the drive side than on the non-drive side. So essentially what I just shown you is what Fulcrum is doing, at least on some of their wheels. The other exception are some Industry 9 cross-country wheels using the same issue as with Fulcrum. They are using simply half the spokes on the non-drive side and on the drive side. No one else, at least to my knowledge, is doing this, and I'm not really surprised, considering that it's a major hurdle trying to get the perfect spoke sizes for each wheel you're making, because if you're a manufacturer, there's really no excuse of making this correctly, especially if you're DT Swiss and you're making the goddamn spokes, so you probably should have made the spokes that are fitting each wheel size, each rim size. You should have this down to the science, and they probably don't, because it's simply simpler to make it with a straight gauge or whatever butted spokes you're using. And let's face it, majority of everything is being sold but not really used, so the warranty claims are probably not as much of an issue for the bigger manufacturers as they are for, I know, small shops or something like that. 4. This is not an original concept. When I was browsing the internet one day, I found an article on the Sheldon Brown's site. It was like 2 or 3 years ago, when essentially the same kind of thinking and the same kind of wheel build process has been described. The author of that particular article, it wasn't Sheldon, I think, was describing how he tried to use a thinner spokes on the non-drive side, and he equalized the tension on each spokes, trying to use them as a string. So he was aiming to have the same sound being emitted by each spoke when it was pinged. Kind of smart, really. Anyhow, this is not an original concept. I'm sure that if I dug even deeper, I would find several, I don't know, references to someone doing something like this, either for bicycles or for something else. 5. And of course, yes, this means that your wheels essentially are either too flimsy, because your drive side spokes are too thin to carry the load of you and whatever you're carrying, or your wheels are too heavy because your non-drive side spokes are too thick to the specification which you should be using. So there you go. And this, I think, is everything I have to say about this subject, because I think I was quite exhaustive, and I'm not really confident that my approach was correct, because I'm not a physicist nor I am a mechanical engineer, and I am now repeating myself, so I'm going to stop. I hope you liked this video. If you have a comment, leave it in the comments. You probably can't leave them anywhere else. I don't know, I don't have a Twitter or anything. Anyhow, if you have a comment, leave it in the comments. If you like this video, then like this video. If you think this video is worth sharing around, then please do. I'm always welcoming this subscription thingy going up. Yeah, it's a kind of a vanity thing. And I hope to see you on the next one. And I'm going to stop talking right now because I'm starting to talk nonsense.